Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the internal normal force, shear force, and moment at points C and D in the simply supported beam. Point D is located just to the left of 2,500 pounds force. So not only are we going to find the internal forces, we are also going to draw the shear force and the bending moment diagram. All right, okay, right. So this problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have a simply supported beam, and it is loaded with a rectangular distributed load from A to 3 feet from A, and we have a point load 3 feet from B. So to start with, quickly let's draw the free body diagram and then start doing the sectioning. Okay, so at the hinge A, we expect the reaction force AY and AX. Then at the roller B, we expect BY. Then we are going to have a distributed force from this rectangular, we are going to have an equivalent force from this rectangular distributed force, and it will be acting mid-span from A, which will be 3 feet. So mid-span of this distributed force. And this magnitude is just the area under this loading diagram, which is equal to the intensity of the load, which is 500, times the length of this rectangular distributed load, which is 6. Therefore, this gives us a 500 by 6 is just a 3,000, right? 3,000 pounds. Great. So then let's start applying the equations of equilibrium. So we have summation of moments about point A equal to 0 and clockwise being our reference. What do we have? We have a 3,000 clockwise, okay, by the lever arm, which is just 3. And then we have 2,500 times 9. And then we have by times 12, right, equal to 0. Therefore, our by will be equal to, let's calculate our by, 3,000 by 3 minus 2,500 by 9 divided by 12. So we have by equal to 2,625 pounds, right? Minus 3,000 by 3 minus 2,500 by 9 divided by 12. Great, 2625. Let's find the vertical component summation of forces in the y equal to 0. Okay, what do we have? We have AY plus BY minus 3,000 minus 2,500 equal to 0. We've already calculated BY, and BY is this one here. Okay, therefore our AY is just going to be equal to, let's find what AY is. So 2625 minus 3,000 minus 2,500. Our AY is equal to 2875, right? 2875 pounds. 2625 minus 3000 minus 2500, 2875. And then finally we have summation of forces in the x direction equal to 0. Of course, we know that our ax is just going to be equal to 0 because we do not have any active force applied in that direction. So ay we said is equal to 0 pounds. Ax is equal to 0 pounds. Ay is equal to 28 75 pounds. And then by is equal to, let's write down by somewhere here. Use black. By is equal to 26 is equal to 26. How come I'm not able to write? It's equal to 2625. Okay, 2625. Great. So we have found all the support reactions. So let's now start making sections. We'll start with C. So we're going to section here. Okay. Then we have the left hand side section and the right hand side section. You go with the one which is simpler. Okay. So I'll go with the left hand side section. Alright, so let's draw it quickly. Of course, it's going to be something like that. Okay, something like that. We have a load on top, distributed load. Going to have a distributed load like so. This point here is C. Okay, and then we have a reaction there of 2875, and then we'll have an equivalent force. We'll have an equivalent force here. What's this length? This length is 3 feet. So we have a shear force there, BC, and we have MC. What else do they want us to find? And also we have a normal force, NC. So this equivalent force is equal to the intensity. The intensity of this load here is 500 pounds per feet. Therefore, this load becomes 500 times the length 3, which is equal to 1500 pounds. Alright, so summation of moments about point C equal to 0 and clockwise being our reference. What do we have? We have a minus 287 times the lever arm 3. Okay, and then we have a plus 1500 times this one is the length here is half mid span of this length, which is just a 1.5 feet. So therefore this is 1500 times 1.5, and then plus MC equal to 0. Therefore our MC will be equal to, let's calculate, it's minus 2875 by 3, and then plus 1500 by 1.5. Therefore our MC is 63.75 pounds feet. Great. Let's move on to the next part. All right, let's create a boundary there. Great. So where are we? So we need now to find the vertical component. So say summation of forces in the y equal to 0, going up in our reference. What do we have? We have 2875 minus 1500 minus VC equal to 0. Therefore, our VC is just going to be equal to 2875 minus 1500. Our VC is going to be equal to 1375 pounds. Right. Are we there? 2875 minus 1500. 1375. Great. And then summation of forces in the x direction. Of course, we know that our NC is just going to be equal to 0 pounds. Great. So let's move on to D. And here they've told us we need to mind because shear will be different on either side of D. So they've told us to find the internal forces to the left of the load 2500. So this is to the left here. Okay. So this is the left hand side and this is the right hand side. Which one are we going to go for? The simplest. Of course, we'll go with the right hand side, right? Of course, but mind, where are we doing the sectioning? We are doing it to the left of 2500. Okay, so it will be included in our section. All right, that's very important. Great. So let's draw our section there. Of course, this point here was A. That was A. So this one here is B. Okay, we have a reaction force there of 2625, and then here we are going to have this load of 2000. Okay, it's going to be there, right? And then this length is 3 feet, and then this point here is D, so we'll have a shear force of VD and a moment of MD and a normal force of ND. Great. Let's apply the equations of equilibrium. So we'll have summation of moments about point D equal to 0 and clockwise being our reference. What do we have? Okay, we have an anti-clockwise moment from 2625 times the lever arm, that's anti-clockwise. What else? Plus minus MD. MD is clockwise there, right? Because of the section that we used. Okay. So finally making MD subject to our formula, MD is just going to be equal to 2625 times 3. This gives us 78, 2625 times 3, 78, 75, 78, 75 pounds feet. And then we have summation of forces in the y equal to 0, going up in our reference. What do we have? We have minus 2500 plus 2625 plus VD equal to 0. Therefore, our VD is just going to be equal to minus 2500 plus 2625. What do we get? We get our shear force of minus 125, right? minus 2500 plus 2625. Great. Pounds. So this minus just indicates change in sign. Okay. All right. And then finally, we have summation of forces in the x direction equal to 0. Of course, we know that our ND is expected to be equal to 0 because we do not have any active force applied in that direction. Great. Let us draw just a boundary so that we use this part of the space for drawing, for working out the drawings that we are supposed to make. So we are going to use the relationship the rate of change of moment with respect to x is equal to shear force, and therefore moment is the area under the shear load diagram. And we also know that the rate of change of shear with respect to x is equal to the distributed force, and therefore shear itself is equal to the area under the load or the distributed load diagram. So having these two relationships or these differential equations, we are going to use them for drawing the shear force and the bending moment diagram. So let's quickly start doing the work. Just let's put up our line work in that manner like so, in that manner like so. So we have the shear force. This is the shear force. This is the shear force diagram, and this is the bending moment diagram. Okay, let me just also just create a boundary here. I create a boundary. All right, something like that. Great. So let's start doing the work. Of course, up here is positive, negative, positive, negative. All right. So at A, we have the boundary condition of AY equal to 20, 28, 75. So we start with that one going up. So let's say that one takes us maybe somewhere there. Let's say that is our value. Okay, somewhere there. Okay, so let's keep it. The value is 28.27 pounds. Great. All right. So what happens from A to, this is A, B, C, D, E. So let's call this point here E. Okay. So what happens from A to E? Our Q there is equal to, is negative, and it is constant, right? Therefore, we expect the slope of our shear dvdx to also be negative and constant. Great. And this magnitude is going to be equal to the area under the distributed load diagram, which is just equal to, because it's rectangular so we can calculate it directly, minus 500 times 6. Okay, so this gives us a minus 3,000, right, pounds. So now we need the two now will interact, okay, so that we know the final destination. So 2875 minus 3,000, what do we get? 2875. 2875, this is 75 here, but who wrote this 27 here? Who was writing these things? Yes, this is what I was writing in my mind. I'm not sure what the hand was doing, so sorry about that. Great. So 2875 minus 3,000, what we have? We have a minus 125. Minus, great. So let's move in the negative direction. Let's move, mind you, When you look at the load, it is constant. Therefore, the shear will be governed by a polynomial of degree what? 1. Great. So let's move. So it will be somewhere there up to, we want to go up to E. E is somewhere here, right? All right, somewhere there. Great. And then from E to D, what do we have? Q is equal to 0, and therefore the slope of our shear dv dx will also just be 0. Okay, so the same value maintains. So from there we are going to move, and this value here, let's take note of it. We say this 125 is minus, down there is minus, we've already indicated. So let's move, constant is like that up to D. D is somewhere there. Okay, up to D somewhere there. Great. Then the moment we reach a D, the two are going to interact. At D there we have minus 125, then minus 2500. What do we get? So minus 125 minus 2500. We get a minus 2625. Okay, so we need to move down by that value. So from minus 125 we'll go down maybe up to somewhere there. This one is not straight enough. All right, up to somewhere there. So that value is a minus, say minus 2625 pounds. Okay, can forget about these units. We all know they are pounds. Okay, so that we just make it uniform. And then later on, let me just clean my slate because I've run out of space. Then later on, we know that from D to B, our Q is equal to 0, and therefore the slope of our shear dV dx is also going to be equal to 0. So we'll just move with a constant slope up to there like this. Then when we arrive there, the two are going to interact algebraically. So we have a minus 2625 plus a positive 2625. This therefore gives us a 0. Therefore we need a what? Closure. Business has to close. Great. Something like that. So this is positive and this is negative. So we've drawn the shear force diagram. We have drawn the shear force diagram. What we need to do now is to draw the bending moment diagram. Okay, let's draw the bending moment diagram. Let me just clean up my slate. So from A to E. All right, before we start, first we need to check the boundary condition. Do we have any couple applied at A? No. Does the support at A resist any moment? No. Right, therefore we expect the moment at A to start from what? 0. Great. So what do we have? So we know that our shear is positive. So there is a slope there. Okay. There is that slope. I mean, there is a point where shear cuts in the x-axis, or where shear is equal to 0. So we need to find that point. It's quite important, that point, because it gives us the maximum moment. So let's find that point. Let's call that point x. Okay. So we can use similarities of triangles, right? So I'll use 125 and 285. So we'll say 125 plus 228.75. Let me, so 125 plus 28.75 divided by the length there, which is 6, is equal to just 125 divided, we're just using symmetries of triangles, okay? So this is a triangle, we are trying to do this triangle here like this, okay? And then with the smaller one there like that, okay? So that's what we are doing. All right, great. So 125 and then divided by, in fact, divided by, let me, instead of finding this, it will be much easier to find, I'll come and subtract that later on. I come and find this one here. This one from there to there, okay? Let me find this. This will be much easier to find. All right. So that I don't increase the work. Okay, so 125 divided by x, and therefore my x is just going to be equal to, let's calculate it, 125 plus 28.75 divided by 6, and then we have 125 divided by 500. Therefore x is equal to 0.25. So this one is equal to 0.25. This x is equal to 0.25. Okay, so if that is the case, therefore we can find this. We just subtract 0.25 minus 3 minus 6, right? Minus 6. So this gives us a 5.75. Great. So having known that, we can now begin doing the work. So we said from A to E, our V is positive and it is decreasing, okay? Therefore, the slope of our moment dm dx will also be positive and decreasing, okay? And this magnitude of the moment is area under the shear load diagram, which is just triangular, so it's half times 28.75 times 5.75. Okay, so once we calculate that, we find the area for that. This is just equal to, so 0.5 times 28.75 times the length, which is 5.75. So this gives us 65.625. Is that so? 0.5 by 28.75 by 5.75. 8265.625. Okay, great. So let's start working. So we expect the slope of our moment to rise. Let me just take this a little bit down. This line, I take it down a little bit, maybe somewhere there. All right. And I also bring this like so. Great. All right. So now let's start doing the drawing. So from from A, we expect a positive and decreasing slope. Okay. So positive and decreasing slope, I know you know already. You know which direction is supposed to go, right? So positive and decreasing, it's going to be like this because it's quadratic. It's a polynomial of degree 3. Okay. So a polynomial of degree 2, quadratic, sorry, up to there. All right. So that point there, we found that point to be equal to 8265.625. Great. And then we expect that continuation for the remaining part. So we've reached the peak. All right. And then we have the region, this region from the peak where we have, let's call this point, maybe we can call it F, where we have the peak. Let's say the peak is somewhere there at F. So let's now continue from F to E. From F to E, V itself is negative and it is increasing. Okay, and our dx, which is the slope of our moment, is also going to be negative and increasing. And its magnitude is just the area under the shear load diagram, which is just equal to half times 0.25 times 125 minus 125. This gives us 0.5 by 0.25 times 125. So this one is minus 15.625. So they will interact the two. So we have 8265.625 minus 15.625. Let's see what we get when the two add up algebraically. So 8265.625 minus 15.625. So we have 8250. So this curve, we expect it to move from there because we are saying the slope is negative and increasing. So we expect it to move down like so, up to there like so. Okay. Like so. Great. This point here, which was the maximum, it is this point here. Okay. Great. So, and then that point there, the new point is 8250. Then from this point to the next point, let me clean my slate. Let's find what that value is. It's going to be linear. So from E to D, what do we have? From E to D, our shear is negative and constant, and our slope dm dx is also negative and constant. All right, and therefore our moment itself is just the area under the shear diagram, which is just equal to minus 125 times the length from E to D, which is just a 3. Okay, so this one gives us a minus 375. So we expect the two to interact. We have minus 375 and then plus 8250. What do we get? 250, we get a 75. So we are going to have a linear, a polynomial of degree 1. From there it will be a straight line, maybe up to somewhere there like that. Okay, let me draw it properly, something like that. All right, and then finally from D to B, of course shear is negative, like in the case it will be like this, also negative and constant, and our slope for moment is negative and constant. So we just need to find the magnitude of dB. We just need to find the magnitude of dB. So let me just indicate it on top here. So dB, what was the magnitude of that one that we found? This one was 78. We need that one. 78, 75. All right. So let's clean up this part, and then we are saying we are on dB, and we also remove this. We just find the magnitude. We need to find the magnitude. We remove this. Great. And therefore its magnitude is area under the shear diagram, which is just equal to minus 2625 times 3. What does this give us? 2625 by 3. We get a 78. We get M is equal to 78.75 minus. Okay. Minus 78.75. So the two interact. So we have a 78 there. 75 minus 78.75 equal to 0. All right. So this therefore is going to close. It's going to close like so. It is going to close. From there we expect a closure. Okay, something like that. This value here, 78.75. Okay. So this is basically about it. This is about it, and this moment here is positive. Right, I guess we are done. Let me just outline the internal forces at C. So at C we had MC of 63.75, and when we look at our moment using this moment diagram, MC, where is MC there? Okay, just before the maximum, for sure it makes sense. VC, it is, we found 1375. Let's check our diagram. All right, 1375. All right, of course it makes sense. And then of course normal force, we didn't even draw any diagram. We are not even expected to, because this is 0. And then for the internal forces, it is the section D. We have MD equal to 78.75, and that one we found it was the exact value there, right? 78.75. And then we had the negative shear at D. We had over 125. Let's check. 125, great. And of course the normal force, as usual, we expected it to be equal to 0. Right. So this is about it, really. This is about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.